Section 11.8, last section of the chapter, conservation of angular momentum. And it tells you from the linear Newton objectives, we have what it's all about, right? When no net external torque acts on a system along a specified axis, apply conservation of angular momentum to relate the initial angular momentum value along that axis to the value at a later instant. That's what we're going to be doing. So let's dig in. Since we have a new version of Newton's second law, and Newton's second law is pretty powerful, we also have a new conservation law that goes hand in hand with it, that if you have an isolated system, then the angular momentum L of that system is a constant. This is the law of conservation of angular momentum, that for an isolated system, which means the net external torque is 0, then the net initial angular momentum must be equal to the net final angular momentum, which is shown here in this Li is equal to Lf. The angular momentum must be conserved. So if the net external torque acting on a system is 0, the angular momentum L of that system remains constant no matter what changes take place within the system. Really cool. So this is similar to our collisions with our linear momentum, but now we can describe some other changes as well. Now, since these are vector equations, they're equivalent to 3 corresponding scalar equations, right? We could write this in multiple directions and it would be true. So we can separate the axes and say, if the component of the net external torque in a system along a certain axis is 0, then the component of the angular momentum of the system along that axis cannot change, no matter what changes take place in the system. So maybe it's only true in the x direction. Well, that's fine. Just work in the x direction. Sweet. Now, something that will happen in a number of examples is that it's possible to have the distribution of mass change with no external torque. And that brings us to this equation, that the initial rotational inertia times the initial angular velocity is equal to the final rotational inertia times the final angular velocity. We're going to see some examples that highlight this, but this is another one of those key equations that really pops up quite a bit. So I hope you'll keep it in mind. So let's look at some examples. Here's one, a student spinning on a stool. You can try this at home if you have a computer chair that rotates about. Please do, or find a chair that rotates around if you can, something that spins. If you start out spinning with your arms out, especially you can hold some heavy things in your arms, like some soup cans or dumbbells if you have them, and then pull your arms in and you will feel a difference. I guarantee it. So please try this out. The rotation will speed up as you pull your arms in, and it will slow down if you pull your arms back out again. So you have brakes built into the system, right? Why is that? Well, it's again, that shift in just the rotational inertia. The mass hasn't changed. You haven't applied a net external torque, but you've moved the mass from being at a really small r to being at a much larger r. You've increased the rotational inertia. So when you increase the rotational inertia, to keep the angular momentum conserved or constant, the angular velocity must decrease. If you instead pull all the mass in, then you're going to decrease the rotational inertia, and to keep the angular momentum constant, your angular velocity will increase. And you see this with ice skaters all the time. They start spinning and they're doing this, and then they pull in and they start spinning faster. It's really cool. You get to be an ice skater if you have a spinning chair of some sort. Please do try this and let me know how it goes. Another example, harder to try at home, springboard diver. So the divers who do the crazy flips, their rotational speed is controlled by tucking their arms and legs in, which reduces the rotational inertia and increases the rotational speed to get all those flips in. But it turns out at the end, it's not that they stop rotating. When they open up just before hitting the water, they have the greatest rotational inertia, so they slow the rotation down, but they have to time the rotation just so that they happen to be pointing down when they enter the water. If they misjudge that height, like say they jump off a board that's actually 10 meters higher, then they will keep rotating and they might do a belly flop into the water because the rotation hasn't stopped. The angular momentum is still conserved here, even in this example. It's just controlled by adjusting the rotational inertia of the body. One more example is a long jumper. So the angular momentum caused by the torque during that initial jump when the long jumper is pushing off the ground, applying a force at some distance from her center of mass, that torque would cause angular momentum, which would cause the long jumper to start to spin like the diver, not desirable in this case. So the angular momentum can be transferred instead to the rotation of the arms by windmilling the arms. So they aren't actually trying to swim and go farther when they swing their arms up around. They're just keeping themselves upright so that they can then fly farther through the air and get some incredible distances. It is another great one to Google. If you find some great GIFs, send them my way, because I obviously am lacking GIFs in this one. Okay. Checkpoint here. A rhinoceros beetle rides the rim of a small disc that rotates like a merry-go-round. If the beetle crawls toward the center of the disc, do the following, each relative to the central axis: increase, decrease, or remain the same for the beetle disc system. A, rotational inertia, B, angular momentum, C, angular speed. What changes? What stays the same, if anything? Think this through. Go ahead and hit pause now. Come up with some answers here. Okay, I'm going to trust that you did that. Well, let's see. What's changing? The beetle is crawling towards the center of the disc. So if the beetle is moving to the center of the disc, then the beetle that has some mass is moving to a smaller r, right? Where we know that I is equal for a particle to mr squared. So the total rotational inertia would be equal to the rotational inertia of the disk plus that of the beetle. Where the beetle is just the mr squared. So if the beetle is going to the center of the disk and decreasing the r, then the rotational inertia of the beetle is going down. So that is decreasing. What about the angular momentum and angular speed? Well, for angular momentum, we have to check, is there a net external torque applied to our beetle disc system? It doesn't mention anything about brakes or a force or friction. So no, sounds like our angular momentum has to stay the same. If our angular momentum has to stay the same, or actually what we could write it is I initial, so omega initial. If it has to stay the same, then the initial must be equal to the final of each of these. That equation that we just saw that I highlighted before. And so if our rotational inertia in the final case has gone down, then what's going to change? Our speed better go up. That beetle is going to be moving a whole lot faster. So sure enough, angular speed does increase there. And that pulls us through chapter 11, where we got to see rolling, an expanded definition of torque, and angular momentum, along with the conservation of angular momentum. Please feel free to ask questions in the discussion, shoot me an email, or stop by my office hours. I would love to chat more.